So here's a case of distributed load, and we got no displacement or rotation at either end. All right, so we'd have some reaction moments on either side, and we have some reaction forces on either side of our element. So it's statically indeterminate, but we can solve with the governing equation for the beam and using the boundary conditions. And the governing equation is omega, which is our distributed load here, equal to EI and the fourth derivative of y respect to x. So again, back further, we already talked about this, what this different equations that we can have for beams here. All right, let's do that. Let's get into this. We're going to integrate. We're going to say it's negative omega because it's a downward force. And we're going to integrate with respect to x. And as a result, we're going to integrate the equation that we have for omega with respect to x. And if we do this, we come up with the third derivative here on the right side. And the left side, we get negative omega x plus c1. Right? This guy right here is our transverse shear equation, right? Equal to v, which again, we talked about back at toward the beginning. So solving for C1, we need a boundary condition, and we can say that our transverse shear is equal to the reaction force at node 1, which is at x equals 0. So plugging in x equals 0 here, and V is equal to R1, we can find that C1 is equal to R1. Right. Keep moving forward here. We're going to take our equation that we had for the transverse shear force, and now we're going to integrate that with respect to x. And if we do that, right, remember that all this was equal to, this was our equation from the previous slide here. So if we integrate that, we get negative 1/2 omega x squared plus the reaction force at node 1, x plus c2. And again, here on the right side, that's our moment. There's our moment equation. So looking to our boundary conditions, we say the internal moment is equal to the negative of the reaction moment at node 1, and that's located at x equals 0. So substituting x equals 0, x equals 0 is bam, bam. So what we got here is C2 is equal to the negative of the reaction moment at node 1. All right, very good. Let's keep going here. So we're going to substitute the equation we just came up with there. All right, integrate that with respect to x. All right, now we got a C3 we need to solve for, but oh, looky here. Right, that is our theta, or angle, times EI. And our theta, our angle, is 0 at x equals 0. So we can substitute for that and solve that. C3 is equal to 0. Right. Last time here, we're going to substitute all the results up into our equation. And now we have this guy's got to solve for C4. And we're getting down here to the deflection of our beam. The deflection is equal to 0 at x equals 0. And therefore C4 is equal to 0. All right, so what I want to highlight here is, once we plug in for C4, we have one equation here that we solve for. And going back here, we also have another equation here once we plug back in for C3, which is 0, so that goes away. So what we have there is two equations with 4 unknowns. So 4 being the reaction force at node 1 and the moment at node 1. Reaction moment at node 1. We also don't know the reaction force at node 2 and the moment at node 2. But right here, we just have the reaction force at node 1 and the moment at node 1. So we can solve for those with those two equations. All right, we need two more boundary conditions, though. We need to, we use the deflection or the angle, the angle at x equal to L. So the other end of the beam there's no rotation. And there's no deflection at that point either. So we can solve for those guys. So substituting those boundary conditions in equations 1 and 2 on the previous slide. We can solve for the reaction force at node 1 and the moment at node 1. And reaction force for distributed load on a beam element is omega, that distributed force, times the length of the beam divided by 2. So it's basically the average, overall average of that distributed force. And the moment then is omega L squared over 12. If we use, go back to the force body diagram, and we substitute in the reaction force, the moment at node 1, using the equilibrium equations, so some of the forces in the y direction and the sum of the moments, we come up with these values. So where the moments reaction force is omega L squared, and the moment is omega L squared over 12. All right. So substituting those in here, we can see the reactions for a uniformly distributed load are these. And actually, it looks like this guy should maybe technically be negative, right? Because if we do right-hand rule on here, this would be a negative directed force there. All right, but these are reaction forces. So if we would reverse the signs of the reaction forces, we'd come up with the external forces or the equivalent nodal loadings, the actual loadings on those nodes for the beam elements. And that's what we can use to solve this. So here's equivalent loadings. This is what we just did here. All right, so we have the distributed load across our whole beam, and we have omega L over 2, omega L squared over 12, and same thing on the other node. If we had a gradually increasing distributed load, we can have the results there already here. Point load in the middle of our beam. All right, so really valuable information in this, and we're going to come back to this stuff in a bit.